All right, so today I want to talk about this little sensor right here. I'll see if I can get this to focus on it. It's a DS18B20, and essentially it will give you temp information for the room that you're inside of. It also gives you humidity information. And what I want to talk about is how I can hook up something like a logic analyzer, though this is a smaller one that I'm actually going to use here. How I can hook this up to the data line on the pen using a probe, connect these two together then, and then I can connect a wire to the logic analyzer, and then I can take the logic analyzer and hook it up to my computer and get a waveform so I can see the actual signal on the line coming out of the temp sensor. And essentially, I'm going to be working on some Python code and some C code with this to trigger a temperature reading, and you're going to actually be able to see the waveform as bits are transmitted and how that's decoded then to give me an actual temperature value. And so that is the value and the awesomeness of a logic analyzer is I don't have to rely on my code to tell me what it's reading. I can also take a look at the waveform, see what it's reading, and compare it to what I think I'm reading in my code to make sure that my code is correct. So let's dive in over here. All right, so I have some C code here to interact with the temp sensor to get readings out of it. And in the main method, the first thing I do here, I reset the bus and then I send a very first command. And this is the read ROM command. The specifics of this are not important. Just know that that's what I'm doing here at the beginning. First, I need to reset the bus, and then I send an initial command. And so now, when I run this, we're going to take a look at the logic analyzer. So that little logic analyzer, a bigger version of it, this thing is reading the actual values on that data line. It's going to show us that data line then in here as it transitions from high to low. It's going to show us that. And so to trigger a sampling of it, I need to run my program, my C program here. So I'll split the screen and I'll do two things. First off, I'll build my C program here, and then I'm going to execute it. But before I execute it over here, I need to hit the start trigger button. So I'm going to capture a waveform here by starting sampling. And then I've also set up the waveform to not start until the line is pulled low, which is the beginning of the sequence. So the line is high when nothing's happening. It gets pulled low. It'll start the sampling then, and you'll see that here. When I run my program over on the right, you can see, there you go. It's already done. It's that fast because the entire sample is all of 12 milliseconds total. All right, so at the very first part here, this is the reset. And of course, I could measure timings in here by clicking with my mouse, and then over in the upper right here, I can see the timing information between falling and rising edges. But I think that's kind of hard to see what's going on and then have to think about the protocol and what that means. So in a logic analyzer, you of course have protocol analyzers you can add. And so over on the right here under analyzers, if I click a plus here and I pick the protocol for the temp sensor, DS18B20, or I can pick one wire. If I go DS18B20 though, it gives me some parameters I can set. I'm using default, so I'll click OK here, and this is on channel 8. There's up to 16 channels you can sample, but I only need one because there's only one data pin. Once I do that, now you can see it marks stuff, and here is the reset condition. So if I zoom in on this, actually, if I click over here on the right, you can see the conditions it detected or the decoded results. First up, we have the reset. And then when I sent the reset, the presence condition is the sensor responding back. So I pull the line low with my C code. I then release it after about 480 microseconds. Yeah, you can see 488 microseconds. It then remains high for a brief period of time. And then within 60 milliseconds, if the sensor is responding, that little temperature sensor I showed you, this little tiny thing here on its data line, it will pull low then. And that is the indication of a sensor being present, which means I can then interact with the sensor. And so now once the reset has taken place, I can move on to the next thing. If you remember, I said I was going to send a command, the read ROM command. That's in my C code over here. This is the next step here, is to send this command. So if you look at the detected results over on the right, there's a ROM command. And it is the read ROM command that I sent. And as you can see here, it marks the various waveforms that are involved in sending this command. And you can actually see the bits here, 1100, 1100. This is actually in reverse. So 0011, 0011. And if you decode that, that turns into hex 433. And so that is the read ROM command. And then of course I can move on here. I sent other commands in my C code. For example, I wait a little bit of time, about 100 microseconds. You should be able to see that in the waveform here. Yeah, 107 microseconds here before I then move on to the next part, which is I need to start reading. In this case, I'm reading the identifier, the serial number for this sensor. So I've got the read ROM response here. By sending read ROM, I'm asking to read the serial number, basically. It responds with the serial number and some other information. And so that's the next thing that was captured here. The first thing it sends is its family code, kind of like a model number. That's a hard-coded value of 28 in hex. It then sends the serial number right here. That's a series of 48 bits. So that would be really hard if I had to look at each one of these and determine is it a 0 or a 1, because if I zoom in here, I'll show you this. On a 0, let me move over. On a 0, to read that, you pull the line low. So the bus or the master, the Raspberry Pi, pulls the line low, and then it releases it within about, I think, 5 microseconds in my code. It needs to at least wait 1 microsecond low. After that time, then the sensor keeps it pulled low, and it remains low. In this case, over on the right, you can see this is 30 microseconds approximately. Because there's a 30 microsecond wait before it then rises again, that means that's a 0. Whereas you can see here with a 1, when I pull low in this case, it's a total of pulling low for 2.875 microseconds. And then it's released, and the sensor doesn't hold it down because it's a 1. It shoots right back up. And so that little short period of time, less than 15 microseconds, means that's a 1. And same thing, so on. So you could imagine if I had to look at all 38 bits of this ROM code, that would take a lot to figure out from the waveform what's what. And so that's why these protocol analyzers are awesome. The last thing here it sends is a CRC then. And then if I want to take this one step further, I haven't done it in my C code yet, but I have done it inside of a Python version of this. So actually, I won't show the Python code. There's no need to see that really. What I'll do is I will come up a directory here where my Python code resides. I'll run my Python code here. Before I do that, though, come over here and I'll start sampling again. It'll wait for that first drop low. Come back here, run my Python code. This should read the, oh no, my Python code's set up to do the same thing. Hold on. Let me fix the Python code to do the entire process here. So let's come over here, grab my Python code. And right now I was testing it versus a C code, so I had to do the same thing. I wanted to actually read the temperature with skip ROM. It's a different command you can send if you don't care to know what the serial number is. Save that. Come back over, we'll run the Python again here, show my protocol analyzer, trigger a sampling to start, come over here, run my Python, and there you go. Now I get a waveform. And in this case, it looks like I had a failure with the Python code. It's a little more time sensitive, so let's do this again here. See if we can get something to work out. All right, there you go. I get a response back with the temperature, and I've got the temperature in Celsius and Fahrenheit, so that's printed out from the Python code. And if I come over here and look at the timing information, what was captured, we have a reset condition, a presence condition, we have skip ROM and convert T. And then it should have continued. You know what? I didn't set my sampling long enough to pick up the temperature here. Let me do this. Let me jump up. I'm going to sample for a longer period of time so I can get the temperature readings as well. Start again. Run my Python one more time here. Hopefully it doesn't crash. Nope, that failed. Let's do it one more time here and get a successful run. Oh, not good luck with the Python today. There you go. Got a reading. The reason I ported my program to C is because timing is much more accurate. At least I can control it with the APIs for timing for GPIO with the C program much better than with Python. But nonetheless, I have a version of Python that does work. Did I not get enough time in here to zoom out and see the full signal? No, it should be capturing it. I wonder why we're not capturing it. All right, so I did some digging here and I discovered there's some issue with the triggering or the time period. I bumped up my sampling up to 50 million samples, which will give me 6 seconds of time. I don't know. Let's do a trigger condition here and see if this works. Let's just see. Python code picks up the temp. Nope. Okay, let's try one more time here. Okay, it's still sampling though. All right, yeah, it's picking everything up here. Let's do this again though. Let's start over. Okay, we got a successful read in Python. Let the sampling finish, or I could hit stop here. I think this will work. There you go. Okay, we've got everything here. Let me zoom out and see how long this was. Oh, that's right. I added a huge 1 second delay in for timing reasons. That's why when I had only 200 kilosamples, that was 25 milliseconds worth of time. And then I think I went to 1 million, which was only 125 milliseconds. So I needed I think I had it on 20 million. No, I had it on 50 million to get 6 seconds. So it's just not a long enough period initially. That's why I'd only read the very first part here, which you have, yeah, there's the reset, presence, skip ROM, convert T. Convert T tells the sensor to take a reading and stick it into what is called the scratch pad. And then I need to send another reset to then read it. And that's why this reset came a second later, which is too long for the previous sampling. But now if I zoom out a little bit here, you can see there's the reset, there's the presence, there's skip ROM, which means I don't care about the serial number. Read the scratch pad comes next. So you can see read scratch pad. That's a command I send. And then I start reading the actual data. And you can see it shows here in the waveform, you can see it shows the temperature, 23.8125. That's in Celsius. Come back over here to the command line. There it is, 23.81. And that's just a rounded version of it. So yeah, you can actually see the very first 2 bytes of data it gets back our temperature. Then there's some thresholds for some other features that are read, but I'm not using those right now. So what I want to show you there is that the logic analyzer can help you see what's happening on the actual wire. And this has been really helpful because sometimes the signal is absolutely correct. The sensor's putting out the right information. And I just had timing problems inside of my Python code or even my C code that I had to fix. So when you're measuring that time, if you have a delay to maybe print something to the screen, that can be too much that it then looks like you're reading a 0 when in fact it's supposed to be a 1. So this has been an invaluable tool to have. So if you're ever working on hardware, or you want to work on device drivers and Linux, which is a great way to have a better understanding and appreciation for devices and buses and how the kernel works, having a logic analyzer with sensors that are external and wiring those up is extraordinarily invaluable because you can take a peek at what's actually happening inside of your circuit without needing to try and set up some other surrogate for measuring what's happening. You can see the actual line values right here on your screen.